in the preceding example, we have just seen an initial velocity that is positive and an initial velocity that's 0. Also note that thing 1 had a final velocity that was 0, yet thing 2 came out of the collision with a final velocity that was not 0. So our plan is to look at this equation now greatly simplified in that collision and see that the mass of thing 1 times the initial velocity of thing 1 is equal to the mass of thing 2 times the final velocity of thing 2. This is the most beautiful, I think, of transfers of momentum. I came in with some momentum, and that guy left with the same momentum. I lost all of my momentum. Did you see that I was pretty much stopped at the end of the experiment? And all of my momentum was transferred over to that other guy. So we've got, well, I guess there's not much else to say. I came in with a certain speed, and he left with the same speed. That means that our masses must be equal also. Let's see if we can get some more examples going. Thank you.
That was an example of a perfectly inelastic equation. And since thing 1's initial velocity was 0, the equation simplifies to and then, since we know that we were moving at the same speed because it was a perfectly inelastic equation, we can write that then this part of the equation simplifies to and then we can factor out the final velocity, and we get that
Right. So if mass 1 comes barreling in, and I like that verb, I think it's one of my favorite verbs. If mass 1 comes barreling into M2, which is sitting at rest, and it's an elastic collision, elastic collisions are the ones that conserve kinetic energy also. So energy is conserved, and of course in every collision momentum is conserved. But if M1 comes barreling into M2, which is just sitting there innocently, then the final velocity of the two masses are given by these equations, which the book says result from simple algebra, and we found result from messy, complicated algebra. But I want to investigate three special cases in this set of equations. And the first situation I want to investigate is, what if M1 equals M2? Well, then we'll find that, remember, M1 is the guy that is actually moving initially. The velocity final of the guy that's moving is going to be, well, instead of writing M2, I'm just going to write M1s everywhere. So I'm going to write M1 minus M1, I'm looking at this equation right here, over M1 plus M1 times V naught. So how fast is that first sucker moving? He comes in and he hits somebody of the exact same mass as he does. The exact same mass that he has, and we're going to find that his velocity is 0. He's stopped then. Interesting. And the final velocity of thing 2, well, that's going to be 2 times m1, remember I'm not going to write m2, and then that's divided by m1 plus m1 times v naught. We can simplify that. Oh, yes we can. This is just 2 times m1. It's 2m1 over 2m1 times v naught, which is v naught. So the first guy comes in with a certain velocity, hits the second guy, the first guy stops, and the second guy goes out with the same velocity. Interesting. Let's look at another special case. And let's consider the case in which the second mass is huge, m2, absolutely enormous. What if m2 is much, much greater than m1? This is sort of like m1 approaches 0. In the limits of calculus and all that stuff, we can be a little bit sloppy about it, but let's consider m1 going to 0. Check this out. The final velocity of thing 1 is going to be, let's see, all these numbers, I'm going to have m1 sort of not be there, if that's okay, because it's going to 0. So I'm going to rewrite the problem, and then I'll be able to look at this a little more carefully. Times the initial velocity. So if m1 goes to 0, then this term is 0, and this term is 0. And it looks like we've got negative m2 over m2 times v naught. And you know that negative m2 over m2 is just negative 1. So this is negative v naught. That says that the final velocity of this thing with extremely small mass, it came up and it hit m2. m2 is honking. m2 is a basketball, and m1 is tennis ball. And m1 comes in, it goes boop, comes back with the same speed as that which with it left. Go like that, yep. And the basketball changes its velocity just a very tiny bit, and the tennis ball changes its velocity quite a bit, and we get this relationship where that's negative v naught. So let's look, let's see how fast v2 is going after the collision. Remember, m2 is the extremely massive object. So that's going to be, check this out. 2m1 divided by m1 plus m2 times v naught. But we're supposed to say that m1 goes to 0. So in fact, to first order, the sloppiest way of looking at this, says that the final velocity of thing 2 is, 2 times 0 divided by m2. 2 times 0 divided by m2 times v naught. Well, that's not going at all. So that's the case if m2 is actually an infinite mass and m1 is any regular mass, or m2 is some regular mass and m1 is nothing at all. Mass 1 will bounce back with its initial velocity, having done nothing to the enormous mass that is resting there, waiting for the attack. So let's do the final example, and I guess you can figure what's going to happen here. I'm just going to switch the order of those two suckers. This is really an interesting thing, though, and there's a beautiful example that goes with this. Now I want the resting thing to be light, and the incoming object to be massive. So we're doing something like this. And I can do that a little bit cleaner in a moment. But I want the thing that's at rest to be light, and the thing that is coming in to be supermassive. So this is like a rhinoceros hitting a fly on the run. And that's pretty interesting. So another way of looking at this is that m2 goes to 0. And you'd be surprised, it's not exactly the opposite, because there's some asymmetry between m1 and m2 over here. So let's look at the final velocity of the massive thing. How does that change? We're going to have m1 minus m2 over m1 plus m2 times v naught, and we're supposed to say m2 goes to 0. So we're going to have m1 over m1 if, as we promised, these guys are going to 0. Check them out. That's 0, and that's 0. So this is m1 over m1 times v naught, which you guys know as v naught. So the initial object, the guy coming in, continues unimpeded at its initial velocity. However, this is just an approximation because we're doing the limit very sloppily. However, I want you to consider what's happening to the final velocity of thing 2. Now we're supposed to do this equation, 2 times m1 over m1 plus m2 times v naught. And notice that if m2 goes to 0, we have 2 times m1. Let me circle what's going to 0 here. That guy's 0 right there. 2 times m1 over m1 times v naught. Oh boy. Oh boy. This says the final velocity of the thing that was at rest is twice as big as the initial velocity of the thing that came barreling in. Feels kind of funny, but I've got a wonderful example of how it works for you. Just need to find my basketball. Okay, so I want you to consider this is a complicated problem, and it will take a moment for this to sink in, but you can watch it a couple times. Hopefully I'll get it to work right away. I want you to consider, as I drop these guys, when the basketball hits, it will return at pretty much the same velocity as the one with which it hit. Watch this. See that? Okay, so it's coming back upward. When the basketball is coming upward, it will run into the tennis ball, which is still kind of going downward. So I want you to watch what happens right now. I'm going to try to do it over here so that you can see it versus the blackboard. Get ready. Holy cow, did you see that? Maybe you want to watch that again. The tennis ball shot up way higher than the basketball initially started. It's that factor of 2 right there. Boom. My momentum was transferred over to that other guy. So we've got, well, I guess there's not much else to say. I came in with a certain speed, and he left with the same speed. That means that our masses must be equal also. See if we can get some more examples going. Thank you. Equation now greatly simplified in that collision, and see that the mass of thing 1 times the initial velocity of thing 1 is equal to the mass of thing 2 times the final velocity of thing 2. This is the most beautiful, I think, of transfers of momentum. I came in with some momentum, and that guy left with the same momentum. I lost all of my momentum. Did you see that I was pretty much stopped at the end of the experiment? And all of my...
That was an example of a perfectly inelastic equation. And since thing 1's initial velocity was 0, the equation simplifies to
in the preceding example, we have just seen an initial velocity that is positive and an initial velocity that's 0. Also note that thing 1 had a final velocity that was 0, yet thing 2 came out of the collision with a final velocity that was not 0. So our plan is to look at this.
And then, since we know that we were moving at the same speed because it was a perfectly inelastic equation, we can write that then this part of the equation simplifies to